All right, without further ado, let's give Christian the floor.
Hello, everybody. So yeah, today I'm going to be walking through a bunch of Markov state model stuff. If you want to follow along yourself, I'm putting in the chat how to do it. So go to this link and then under the supplementary info file. What did we call it here? In Jupyter notebook. If you want to follow along, but I'll also be sharing my screen and going through all the stuff myself. So you don't need to, just whatever is going to work best for you. So you can either download that and just look at it as I talk through stuff, or just follow the screen as I talk through stuff. I'll just give a little bit of time. So if people do want to download that, they can download that and pull it up. Just a little bit more. But yeah, as people are coming on and downloading that if they want to, I can talk a little bit about some overview of Markov state model stuff, and also a bit of what I'm going to go into today. So certainly for people that haven't done Markov state modeling before, and probably even for those that have done some before, it's not going to be particularly helpful to focus on every single detail that I am talking about. I think it's going to be a lot more useful to try to get an overview of what this can be used for, what are some of its strengths and limitations, and what are some things in general to be looking out for if you start creating your own models, so that once, for example, if you want to start building Markov state models, hopefully you could remember that, oh, I should look into this thing when I'm building it. I should try to keep in mind this factor as well, because I don't think it's reasonable to remember the exact details, but as long as you remember, oh, I should look out for this, then when that time comes, you can look it up again and go over the exact details there. So I know there's still a couple more people that are coming on. For those that are coming on, if you want to follow along yourself, you can download the Jupyter Notebook through the link that I sent in the chat, but I'll also be sharing my screen so you can just follow that instead. With that, I will start sharing my screen. Yeah, so I'll go over one of the Jupyter notebooks that we presented in that recent paper. But first of all, I'll talk a little bit about Markov state models in general. So some of you have definitely heard about it. Some of you, I think, have some more experience than others with them. But in general, what can they be used for? Do any of you have ideas, thoughts from what you've heard so far from other people? What do you think their use is?
I can go ahead.
Please do.
Just because I just gave my presentation.
Please do.
Yeah, we can calculate kinetic rates from the Markov state model, which is pretty useful for many systems that we are studying in the group.
Yeah, thank you, Kevin. He's exactly right. So one of the big uses of Markov state models is that you can calculate kinetic rates between different conformational states of proteins. So what you can do through molecular dynamics is you can sort of examine these different conformational states that a protein may pass through, you can cluster them into different groups based on whatever you're interested in looking at. But through molecular dynamics, you can't necessarily get quantitative transition rates between these different states. So qualitatively, you'd be able to see that, oh, a protein can exist in this state, it can move to this other state. But for example, if you start your molecular dynamics simulation in one state, and by 300 nanoseconds, it transitions to a second state, that doesn't necessarily mean that every single time this protein is going to transition in 300 nanoseconds. Because you're just doing one replicate, one copy of a system, and that's not enough to get any sort of statistical significance of how quickly this transition is happening. But through Markov state modeling, then you can get statistically significant transition rates between different systems. So that's a bit of overview. And then as I go through all of this, please stop whenever you have questions and ask me, either put it in the chat, unmute yourself, whatnot, because we'll be going through pretty disparate sort of stuff. So just ask your questions whenever they arrive. Don't wait until the end. So there are a few different softwares that you can use for Markov state modeling. I'm going to talk about this one called pyEMMA right here, just because I have more experience with it. But there are others out there. For example, MSM Builder is another popular one. Again, this notebook is published online, so you can download it whenever you want to start doing your own Markov state modeling stuff. You can just copy whatever you find useful for it. So here we've imported the pyEMMA environment, some very helpful stuff from Abby about how to make the figures larger and better resolution and so on, and then just some useful stuff, that will be needed later on. So the first thing that you'd need to do before you even get to this stage is you do need a lot of input data to create Markov state models. So a big way that you can sort of think about Markov state modeling is it's a very different way of clustering than you might be used to. So through molecular dynamics, you can cluster different conformational states. Markov state modeling is a very different way of clustering states and then just getting transitions between them. But for both of these two methods, you do need a lot of input data. So what you'd first need to do is you'd need to run relatively long molecular dynamic simulations. And then here is where we would be loading those trajectories. And definitely a common question is, how long of simulations do you need to run to create a Markov state model? And there is honestly no answer for that. Certainly the longer, the better. And you need to run one long enough until you reach statistical significance. And then you'd ask, okay, well, how long do you have to run to reach statistical significance? That is going to depend upon the specific transitions that you're looking at and the length of those transitions, which you aren't going to know until you build your model, start trying to examine whether it passes a bunch of statistical tests. So there isn't necessarily a way of knowing this until you've created a model and started running these tests on it. Just to give very general advice, you're definitely going to need trajectories in the microseconds, probably in the at least tens of microseconds if you have small transitions, and then probably hundreds of microseconds if you have bigger transitions. Just to give bigger overviews, but certainly it depends on the system and the exact transitions that you are looking at. Okay, so that is the input data here. Yeah, let's move on from that. Okay, so once you've run your molecular dynamics simulations, then you import them into your notebook, and then you would want to figure out what transitions you're interested in looking at. So, you know, with normal molecular dynamics clustering, you would probably do some RMSD criteria. So you would cluster everything within some, let's say, 3 angstroms of each other in one cluster, everything within 3 angstroms in another cluster, and so on. So you'd use RMSD as your clustering feature, and specifically differences in RMSD as your clustering feature to separate the different clusters. Clustering through Markov state modeling is a bit different. What you are doing instead of, what you would want to do instead of one feature that encompasses the entire system is you would want to look at some feature, or preferably features, that will maximize the variance in your system. So for the people that have done weighted ensemble trajectories, it's my understanding that it is similar to a reaction coordinate there, where you want to pick some coordinate where you're maximizing the variance. And so for the people that haven't done Markov state modeling or weighted ensemble work, you can think of this as some feature where you're trying to get the biggest differences possible. So let's say you have, let's say your protein starts fully folded, kind of like this. And let's say these are 2 residues right here. One feature that you could think of using is finding a distance criterion between these 2 residues and then maximizing that distance, so that if you see your protein making some big conformational transition to some open state like this, then now you have a much bigger variance between these 2 residues, and thus you've maximized that feature. So that would be one way to go from sort of this conformation of a protein to this conformation of a protein. So you need to know what conformational transition you're interested in beforehand. I mean, there is a way that you can create Markov state models with just picking general features, which will then maximize the variance of anything in your system, but that isn't necessarily going to be some conformational transition that you're actually interested in. So you'd want to look at your molecular dynamics trajectories, pick out what conformational transition interests you, and then try to come up with features that will maximize the variance to select those different conformations at both the starting and then the end state of your trajectories, or of your clustering, however you want to think about it. And so there's a variety of different features that you can make and how you can create them. I'll just pop over to a different notebook here because it's a little bit easier to see. So here, I'm creating some different features where I'm just looking at pairs of residues, and I am looking at whatever is the greatest variance between these pairs of residues. So this is going to be a distance criteria. What is the maximum distance between these residues? You can also do other sort of things. For example, look at backbone torsions between these few residues, see which sort of maximizing the variance in the twisting of these residues. You can also look at RMSD criteria, a variety of different things that you can find in the pyEMMA documentation. In addition, what I've specifically done here, because there's a very difficult system whose transitions didn't work with the normal features that I found online, is you can create your own features. So what I did down here is I've selected some different groupings of residues and then looked at, I've selected these groups of residues, created the center of mass of these different residues in this line here, and then in all this mess of stuff up here, I've then found the maximum distance between these center of masses. And so again, it's really not important to look at details of how I've done this, but just more generally realize, okay, if I'm interested in some features and I'm trying to use the ones that I see in the documentation and they don't describe my system very well, you can create your own features with whatever seems to be intuitive to you. And another question that I do sometimes get is, how do I know what are the correct features for my system? And similarly to the question of how long of trajectories do I need to make a Markov state model, there isn't necessarily a correct answer for which features do I need for my system. In general, you just need to pick features that are going to describe the conformational transitions. And when you think about this biologically, there can be several different features that would be able to describe the exact same conformational transition. So for example, if we go back to this example that I was talking about before, we have one residue here, and then, for example, these three are residues right here. You could try to maximize the distance between my thumb and my middle finger. That could be one reaction coordinate. However, what if you want to maximize the distance between my thumb and my pointer finger? When your protein goes from this state to this state, you're still doing a good job of maximizing the distance between the thumb and the pointer finger, just as you're maximizing the distance between the thumb and the middle finger. So both of these features, thumb and pointer finger, thumb and middle finger, these are both good features to use, and one isn't necessarily better than the other because they're both describing the transition that you're interested in. And so that's a very simple case, but when you think about all the different transitions that can be possible, you'll realize that there's a lot of different features that can be used for describing the same motion, and some aren't necessarily any better than the other. In practice, the ones that visually look like they're maximizing the variance won't always be the ones that are physically maximizing all the variance. So you probably would need to do some iteration there of testing out different features that seem reasonable biologically, and then run through all the statistical tests to see which ones are statistically relevant. So when I would set up some arbitrary Markov state model, I would download my molecular dynamics trajectories, look at them to see which conformational transitions I want to use, and then start making notes of which are all the different features that I could use to describe the exact same motion. And then I'll start playing around with them in my Jupyter notebook. I'll create some features, run that through the Markov state model process, see how well it passes all the tests, maybe try some other features if it doesn't look so well. Because all these are just getting at the same sort of thing of trying to build a statistically relevant Markov state model. Do you have any questions about what I've elaborated about so far before I move on? Okay, if we do not have any questions, we'll keep going. There's not a whole lot going on here. This cell is just showing that once you load your trajectories, now you're assigning these features that you've created above to the trajectories that you had just made. What some people want to do, and also what I've done here, is I'm comparing the same features across a set of two different trajectories. That's often an interesting thing to do, so you can see how things might change between two sets of trajectories. So here I have two different strains of a virus, so there certainly are some mutations that have gone on in between these two strains, and I'm interested in seeing if these affect the conformational transitions that I am looking at. I know what some other people have done is looked at just point mutations that are known to be interesting biologically, and then create Markov state models with the same sort of features across these two different trajectories to see how the point mutation will affect conformational transitions. For example, if there's some point mutation that is known to cause some to cause some protein to behave aberrantly, that could be interesting to look at through a Markov state model. Here, these trajectories were created with the same time step. If they weren't created with the same time step, which I believe is the case over here. Yeah, so for example, this first set of trajectories was not created with the same time step as these other two. You can just use a stride, so then all of the trajectories are being loaded in with the same time step, which you'd want so you can make direct comparisons later on. Okay, so once you've loaded those in, throughout the notebook, you will see that there are a bunch of different cells where I'm saving what I've done so far and then promptly loading it again, just to be helpful. I will say these generally aren't necessary until you get to clustering parts, because these clustering algorithms are not deterministic, which means that each time that you run a clustering algorithm, you could get slightly different results. You still should come to the same conclusion, but the exact results might be slightly different. And so the reason why you would want to save your work after doing the clustering is, for example, if you run a clustering, you make a figure that displays some output of your clustering, and then you realize you need to change one color on the figure. If you rerun the clustering, now all of a sudden you get some different figure, and maybe there are some numbers from the figure that you had written about. Then now you need to change those specific numbers as well. And so even if you're not changing your conclusions, it does get to be quite a hassle to keep having to change specifics about your clustering. So it's much easier if after you run the clustering later on to just save what you've done, and then if you need to change anything, reopen the completed clustering and then make changes to figures or whatever you need to do. So the first dimensionality reduction. Ooh, we have a question here. Oh, thanks. The first thing after you loaded in all this stuff is we're going to use TICA, which is it is a method of reducing the dimensionality of your whole data set to some components. So for people who have done PCA, you can think of this similar to principal components. So TICA components are just coordinates that can be some combination of atoms and then of, for example, distances and whatnot in different weights between atoms to describe some motion. And you'll want to do this because loading in an entire trajectory contains an enormous amount of dimensions, and you want to reduce it to some very small number of dimensions that you can start to examine the variance of going forwards. And so what this is doing is it takes the features that you had previously created and is going to make components based off of those features with the lag time that you input. So lag time, you can think of it similar or analogously to a time step in a molecular dynamics trajectory. So in a molecular dynamics trajectory, you put in the time step to determine how much time is moving forward between frames of your system. In Markov state modeling, your lag time is going to be how much time is moving forward in between. How do I describe this? It's the amount of time that's going to be moving in between where your conformational transitions are sampled. And so there are arguments for making either shorter lag times or longer lag times. So when you have shorter lag times, you're sort of sampling this transition more. And so you should be able to get, as presuming that you're doing enough sampling, you should be able to make sure that you are covering the entire transition. Do you have a question here?
Oh, sorry.
Okay, so the lag time is going to, you'd want to make sure you get a short enough lag time so that you are sampling the entire conformational transition. However, if you get longer lag times, then you can perhaps sample longer conformational transitions that would be happening on much longer time scales. So it is a bit tricky to decide what sort of lag time you want. We do have some tests that I'll go into later on to help determine what lag time you should be using. So okay, you've picked your lag time, just some stuff to sort of reformat the data. And here, again, because I am trying to compare between two different data sets, I want to make sure that they are using the same dimension. So I've just printed out some stuff to make sure that that is happening. That's actually being done here, sorry. So okay, they have some different number of frames that I use in input data, but they are using the same internal coordinates, the TICA coordinates. Okay, so now that I've loaded in my data, I've created the features that I'm interested in, and I have selected some internal coordinates for them. I want to see if these internal coordinates are displaying some conformational transitions. And so a very quick and dirty way of doing this is to just plot what these internal coordinates are doing over a function of time. And so this is a qualitative way of just seeing, okay, are there transitions here? So here you see that there are a bunch of transitions that are happening. And so this suggests that, okay, these features that I've selected are showing transitions, and let's move forward and keep going. If this line was essentially just straight all the way across from left to right, that would say, okay, the features that you're selecting aren't showing any sort of transitions, so stop at this point, go back to the start, and select some new features. So this is just a qualitative test. As long as there's a bunch of bumpy, jagged lines, this passes, and let's move on. Okay, again, saving all my data, moving forward. So here's the first clustering that we're going to do through some k-means clustering. You see right away that I've saved that. There isn't a whole lot to say here. These are relatively standard. Really, the only thing that you would change is you change the job number to the number of processors that you have, to twice the number of processors that you have on your system, just for speed purposes. Okay, so you have done that clustering. Now, there are a few different types of Markov state models that you can create. There are sort of the original or vanilla Markov state models. A bit more recently than the pyEMMA developers have created Bayesian Markov state models, which should have a bit better sampling included in how the clustering is made. So those are supposed to be a little bit better than general Markov state models. In practice, I really haven't seen much of a difference. You can also do these things called hidden Markov models, where you would take a more normal Markov model and then coarse grain that to look at different transitions that you can't see in your normal Markov model. In practice, I haven't found that this has worked very well. I know some other people in the group have had good success creating hidden Markov models. I was actually just on Friday having an interesting conversation with Oslam about this, because both of us had a lot of issues trying to create hidden Markov models with large amounts of data, and in our two cases, it appeared that using less data would create a better coarse graining for the hidden Markov model, but there really isn't info online that we can learn about this. So for my case, I could not create a good one, and I'll show you what that looks like, because sometimes it's interesting to see things that fail and to at least see what this looks like in case it happens to you. So what I have done here is I've just loaded in the trajectories that I picked above. I told it how many different states I want to cluster into, and then this is going to be the first statistical test. So, and you can see there's a bunch of errors that it's talking about, but what does this look like? So what we have here are transition timescales on the y-axis, and then down here we have our lag time. Actually, one thing I should have noted earlier is that you can use either a lag time or you can do some conversion to use nanoseconds instead if you prefer that for your time step. But there is a direct conversion between them based on whatever is the input time step of your trajectories. So, so here I'm using lag time, but just note that we can convert this to nanoseconds very easily. So what do we have here? First of all, in this dark gray region, that's a forbidden region of transitions that are not statistically possible because they are transitions that are happening faster than the lag time that you chose. So for example, if you choose some lag time that would correspond to 10 seconds, and there's a conformational transition that happens in 5 seconds, you can't physically see a 5 nanosecond transition happening when you're only examining the system every 10 nanoseconds. So this region is showing this dark gray region is showing which transitions are not physically possible. Then these lines up here are going to be lines for each of the different conformational transitions that are being selected for in this Markov state model. And what you want to see is you want to see these lines gently rise and then level off, hopefully quickly, but at least by the end, you want them to be nice and level and stable. And so this looks like a mess because it is a mess. So this first line, it goes up to, what would that be? I don't know, 150 steps, and then it has a full break until whatever this step is. That's terrible. The second red line, it goes a bit further and then stops. That's not what we want either. This green line, it is jumping all around and then seems to sort of break around here. The blue one goes a bit further and then just plummets into the forbidden region. So this is all quite terrible. This is not some smooth lines that are rising and then nicely leveling off. And so if you see this, what you'd want to do is you would want to start to try out different features, try out different lag times to see if you can pass this test. I could not do it for a hidden Markov model for the system with a whole number of tries, and I was getting my normal Markov models to work. So I just moved forward with those. So this is called the implied timescale plot or implied timescale test. And this is the first measure to make sure, first of all, that the transitions that you're examining are not going to be faster than the lag time that you've chosen, and that these transitions are going to be sort of smooth and steady transitions and not ones that are jumping all over the place, which would then be really difficult to sample. So from there, I created just a normal Markov model, and these certainly look better. So again, we see that nothing is moving into this forbidden region. These lines are much smoother, they're much more discrete. This one is still rising a bit, which is not optimal, but it's at least coming much closer to leveling off than the ones that I just showed you where they're jumping all over the place. So this looks much better. And from there, let's move forward to the next tests and the next systems. From here, so okay, I showed that the transitions that I'm looking at seem to be relatively smooth and that there are a few different transitions that are happening. So I know one thing that Aslam was asking is, okay, what do these different lines mean? I see 5 of them here. What is that? So that's showing that at least 5 of these conformational transitions based off of features that you selected are going to be feasible to see within the time set that you've chosen. So there are some different conformational transitions that are happening. So from this stage, you could say, okay, there's at least 5 different conformational transitions that are happening. From there, we can look a bit closer into each of these conformational transitions. This is actually, sorry, 6 conformational transitions because each of these lines represents a transition between 2 states. So at least these different transitions and states, we can examine into each one of them and see if this is physically describing what we want to be seeing. Another sort of qualitative thing that we can do is we can take those states that we just examined above and look at the timescale separation between these states to see which ones have a lot of variance between the 2 different states. So each of these dots represents some transition between 2 states, and you would want to have a high timescale separation between these states because a high separation means that there is some conformational transition that is happening. If you have very little separation between 2 states in a system, then there isn't much of a transition that is happening. So the standard is you'd want a timescale separation above about 1.5. So this is saying that the first 2 transitions do have a high timescale separation, and those should be ones that you should investigate going forwards. The next bunch of separations, I plugged quite a lot here. All of them have much lower levels of separation between the states, and so they probably aren't as interesting to look at. This is just a qualitative thing. It's not something that you have to listen to. And so, for example, in some other projects, I might have seen that there are more transitions that seem to have big timescale separations, which is good, but then they might fail other tests later on. So you might have to discard those. But this is at least suggesting that, okay, there's 2 different transitions that are happening that should be worthwhile to look into. So this is the last and probably most difficult statistical test that you would need to have your transitions pass to be counted as valid. So I mentioned just above that in our implied timescale plot, we see 1, 2, 3, 4, 5 different transitions that are all above the forbidden region and should be worthwhile to look at. So those are the ones that pass that test. When I look at the timescale separation plot, I see there's only 2 of those that seem to have a good amount of variance in them, a good amount of separation between these states. And so on a first pass, at least, I would then pick just 2 states, 2 transitions for the final statistical test and see if they pass these. These ones do pass. They look honestly very nice. So we can go forward with these 2 different states. But why do these look good? So what you have, it's honestly quite difficult to see here. You might be able to see a little bit better in these plots below, is you have a solid line, your estimate, and then a dotted line, which will have some blue shading on either side. So the dotted line is the prediction, and then that will be the blue shading is going to be the error inherent in the prediction. So what do these actually mean? When we created our Markov state model, I selected a lag time of 250 steps. I think I can show you where that is. Yeah, selected my lag time of 250 steps. And again, that is chosen just through iteration of what is going to still show conformational transitions that I'm interested in, while still passing these statistical tests. Okay, so if we have a time step of 250 steps, then we go down here to our CK test, which is Chapman-Kolmogorov test, and we'll see that the black line estimate, it's going to go from 0 to the lag time of what we selected, 250 steps, and then from there it'll make some change and go out to infinity, essentially. So that is always going to happen. And then what we want for a prediction is, what the prediction does is it samples at your lag time and then tries to see if, starting from that lag time, do you get the exact same movements sampling at each of these different multiples of the lag time, as if you were to just take estimates at each of those lag times. So it may be a little confusing. So what I mean is that if you take your system and you look at the confirmation, for example, at 250 steps, 400, 500 steps, 750 steps, so on, then you have some ideas of what this is supposed to look like. Then what your prediction does to see if this is a good model that you're creating is your prediction takes the model that you've created. It starts it at 250 steps, and then instead of directly examining your system at 500 steps, 750 steps, 1,000 steps, and so on, it takes the model that you've created, and then from that information, sort of guesses what is supposed to be happening at 500 steps, and guesses what's supposed to be happening at 750 steps, 1,000 steps, and so on. And so if your guesses match if your guesses, which will be on the dotted line, are matching what is physically happening when you directly sample on the estimated line, that means that your model is a good model and it is capable of accurately predicting what is going to be happening in multiples of this lag time, and thus be able to show that the conformational transitions that you're interested in are worthwhile. And so the way to think about this biologically is, again, if you started in one conformation of a protein and you want to sort of walk along the reaction coordinate to a different conformation, you need to make sure that these time steps that you are creating are worthwhile and statistically relevant time steps. And so this is showing that, okay, the time steps that I've selected are going to be good estimates of what this protein is actually doing. So these look quite good, and the way to determine if these pass the CK test is that you want these lines to be overlapping up to 3 times at 3 times whatever your lag time is. So again, I selected a lag time of 250 steps. You can see that these lines are overlapping out to 750 steps, which I show here. So if I had stopped this plot right at, for example, 500 steps, I wouldn't be able to make any sort of conclusions here. If I were to extend the plot out to, let's say, 2,000 steps, and these lines are diverging, it's okay as long as they're diverging after 750 steps. Again, 3 times the lag time. That's what you need to pass. They also pass for my other system. That's great. So with that, once they pass the CK test, that means that the Markov state model that you've created is worthwhile, valid, and now you can start doing fun stuff with it. So, so I've created a nice Markov state model. Here I want to look at the stationary distribution of this model. So what that is taking the model that you've created, what percentage of the clustering is in one state and what is in what percentage is in the other state. So again, for my system, I just took 2 states, but for different people's systems, they might need some different number of states. Here we can see that 52% is in state 1, 49%, or sorry, 48% is in state 2. Until we look at the structures that are in each of these states, I won't necessarily be able to say what these mean, but with the structures, then you can get more interesting information. With these different states, now we can calculate the kinetics that Kevin was talking about at the start to look at those kinetic transitions between these different states. So there's ways that you can do it right here to look at kinetic transitions, but you can also look at these transitions with error bars, which I've done down here. So here you can see transition time between this first state and the second state in the first set of trajectories is around 404 nanoseconds with some error bar. The transition time between the second state back to the first state is a little bit longer, about 438 nanoseconds. So here you can get transitions between 2 states. If you have 3 states, you get transition times between all of these different states, and so on. So then again, I'm saving all of this stuff that I've done and moving forward to one of the last steps here. So I've created a nice Markov state model. I've looked at the transition times between these different states. Now I want to know what these different states actually mean. So again, I'm selecting the number of states that I had picked above. And here I am looking at what is the confidence that the structures that I'm trying to extract are going to be assigned to the states that I'm choosing. So when you run normal molecular dynamics trajectories and you do, for example, RMSD clustering, this is some discrete clustering where these structures are assigned to different states, and they will be assigned with 100% confidence to one state or another. I'm not going to go into any of the background of this, but through Markov state modeling, they use a more fuzzy clustering algorithm where these structures are not going to be assigned with 100% confidence to one of these conformational states. They're assigned with some other percent confidence. And what you can do here is you can institute cutoffs of what confidence you want to see your states assigned to. And so you would obviously want to look at whatever is the highest confidence structures that are assigned to one of your 2 states. And so here I have very, very high confidence in the structures that are assigned to my states. They're at like 99.99999% confidence. So very confident that these are being assigned correctly. When you have lower levels of sampling, you won't have as much confidence that your clustering is assigning with high confidence. So your structures might be assigned to the wrong conformational state, which you don't want. So you'd want to make sure that you're just selecting whatever is the highest number, the highest percentage of confidence here. And the reason why you do this is because when you import your molecular dynamics trajectory and you start creating your Markov state model, the first passive clustering will assign your trajectory into hundreds of different small structural ensembles, and then it'll start to cluster those structural ensembles into much bigger clusters. So here I have just 2 large clusters here into which I've assigned hundreds of smaller structural states. And so, okay, if I just have 2 large states and hundreds of smaller states, how do I know which of those small states to look at that is supposed to be representative of whatever is the conformational state of these 2 different states? So that's why you'd want to pick whatever is a state that's assigned with the highest confidence, and look at what that looks like structurally. So here you again just need to play around with this until you find out whatever is the highest confidence level that you can extract some state. Then you can save those states out as PDB structures. You can open them up in whatever visualization program you're interested in. And if you happen to need those states back in your original trajectories, you can also print out information on where you found them. So for example, in this set of work, I've taken a bunch of trajectories that already have all of their solvent removed from them, just for the sake of space, because loading in trajectories with solvent is obviously going to take much longer than stuff without solvent. And already with the amount of sampling that I have in here, it takes hours or even days to load in those trajectories. And so having ones with solvent would probably make it take a week or more, which really is too long. So these trajectories all don't have solvent, but let's say I'm interested in what the water is doing in some structural state. We can see that for this large functional state, state 0, because it starts at 0 indexing, it's then selected the smaller clustering from this number of the smaller state. And here we have which input trajectory and which frame this was all created from, which then if we go further down, okay, it's not there, but I can show you on this notebook what that looks like. So for example, I can look back at whatever is input trajectory that it listed above. So here we have 25. Okay, that number doesn't mean anything really, but then when for example, if we look at trajectory 62, then I can print out what is the input DCD file that would have the solvent associated with it. So that's how you can then extract whatever are the full state of your system, if you're interested in that. Yeah, there's also a bit more work that you could do if you're interested in looking at the energy landscape. Suppose I can show that. Yeah, you can also look at the free energy landscape of your system. It's just a little bit tricky to look at that because this can only be done on some two-dimensional plot, but if you are running Markov state modeling, you're probably using more than 2 dimensions in your dimensionality reduction. So for example, in this project, I think we have 13 dimensions. So this is a 2D plot of the 2 most important coordinates displayed in terms of the free energy landscape. And then each of these dots is showing which parts of this landscape are appropriately sampled. You just need to read this with care because again, you're only looking at 2 dimensions out of the 13 or however many I end up choosing for this system. But this is some way that you can make sure that you are accessing the free energy landscape of your system and that you're appropriately sampling all of that. I just didn't run that cell, but we have the code right here to do it. So yeah, that's a big overview of how you can start from your input trajectories, select different features that will appropriately describe the motions going on in your trajectories, go through a few different ways of seeing if these trajectories are going to be statistically significant and relevant, and then look at the kinetics, the transition timescales between these different states, and then finally extract those states and look at how well you're covering the free energy landscape for your system. So I know that's an enormous amount of information, but do you all have any questions with what I've talked about so far?
I can go ahead, Christian.
Yeah, go for it.
Yeah, thank you for this very instructive tutorial that you gave us.
Thanks.
It's very useful, and I know it's a lot of work, and we know that you also work so hard with that paper.
Thanks.
And I'm curious on how long does it take for you to finish all this process? Because for the weighted ensemble, it took us also a long time just optimizing the progress coordinate. I bet that would be the situation also for the feature selection.
Yeah, that's definitely a good question. Certainly the longest amount of time is going to be in sort of optimizing the features and then the lag times. So again, the features are, going to be these coordinates to describe the conformational transitions, but then with each different set of features that you choose, there could be different lag times that will work better or worse for each of those. So what I would do is I would look at my system, try to think about, okay, what makes sense biologically or chemically for a feature, put in that feature, and then start testing out a variety of different lag times to see if any of these are going to work. If I can't get any of those to work, then I go back to the features, create a new feature, new sets of features, then start testing out all the different lag times and so on. And I guess one thing, I don't know if it's intuitive or not, but every different feature that you create is then going to, you'd need to retest all of the lag times that you're interested in. So let's say you start off with 5 features, you test all your lag times and none of them work well, none of them pass statistical significance. Okay, if you eliminate one feature or you add one feature, even though you've already run tests for the other 4, you then need to retest your entire model because the dimensionality reduction is taking a linear combination of all of your features. So when you add even one feature to any number or subtract one feature from any number, now your linear combinations are completely different than before. So you then need to retest everything. So yeah, that certainly is where most of the time goes. Once you have that all set, then just running the notebook doesn't take all that long. I would say maybe a day or 2 once you have everything all set.
Okay, wow, it must be a long journey. So can you give us a benchmark with the NA and HA on how long did it take you to come up with a soft spot of feature selection?
I would say that took at least 10 months to do. Yeah, around 10 months or so of iterations.
Crazy, huh?
Yeah. But hopefully it'll be easier for all the next people doing it, because certainly some amount of that time was creating these notebooks and then trying to write in all the comments of what stuff means. Because when I looked at documentation and other work, a lot of it I didn't feel was appropriately documented, so I couldn't necessarily copy it and understand, okay, what am I actually doing here? So hopefully for all of you, if you want to start, you will at least have a bigger head start than when I did. So hopefully it won't take us long.
It's very helpful.
Thanks.
So last question for me. So do we also need to have, do we need to run this to Hopper or some other supercomputers that our lab has access, or can our own workstation can do that?
That certainly is a great question. So your input molecular dynamics trajectories would probably be on Hopper or a supercomputer. I know some people do have good enough workstations that they can generate a whole lot of sampling there. But then once you get those, this running the Jupyter notebook and creating the Markov state model would probably need to be done on your local workstation. Just the one thing that you definitely need to keep in mind is if we go back here to this part. So let's say the trajectories that you want to use for your Markov state model are 10 gigabytes. I think all of us have big enough workstations that we can load in 10 gigabytes of data. However, when you're in this step, when you're loading in your trajectories and then assigning features to them, this 10 gigabytes can grow to some much larger number depending on what features you have chosen. And so this can be the part where you could run into issues if you don't have enough memory on your system. And so what I would do when I was testing out different features is I would start to run this step and then keep a close eye on the memory of my system. So for example, right now in one of these, I've loaded in close to 300 gigabytes of data just from these input trajectories. And so that's the part where you need to watch out. I suppose you could run it elsewhere, but I certainly think with how often you'd want to be iterating through these, it would be a lot easier if you could do it on your systems. I know depending on which workstation you all have, some of them, it's very easy and cheap to upgrade the memory. So then, for example, if you run out of memory, perhaps Romy or Andy could pay for a cheap upgrade. If not, you might need to borrow somebody else's system or trade systems or talk with Andy Romy on how to get enough memory for that. But I would recommend doing it on your workstation. I think is easier than trying to run these through Jupyter notebooks and accessing all of the trajectories elsewhere. I think that would get to be quite a hassle. So that's a good question.
Very useful. Thank you, Christian.
Yeah, of course. I think we had a question. Yeah, question in the chat from Marcus. Okay, so Marcus is saying, it seems like getting enough sampling is generally one of the major bottlenecks. Using an accelerated sampling technique such as GAMD would render the MSM non-valid, correct? That is certainly a good question. I am unclear if anybody has explored this in literature or not. I don't know. I don't know if that would render it invalid, because I can think of arguments for both ways. I mean, why would it be valid? Well, if you're just giving it, if you're giving your Markov model just some arbitrary number of structures and telling it to look at transitions between these structures, then it shouldn't matter so much how you're generating the structures. But yeah, if you're biasing where these structures are going, then yeah, then it might not be so valid to look at transitions between them. I will say I genuinely don't know the answer to that question. I think it's a great one. I don't know actually. Yeah, okay, so Marcus is saying it could be valid if you use reweighting on Tika components. I know, and Marcus, I think that you use GAMD, it sounds like, as well, so you'd probably know that for the rest of the people, you can use reweighting on Gaussian accelerated molecular dynamics for systems that have, I think, under 100 amino acids or so. Then you can appropriately reweight it, and then there certainly wouldn't be any issues. Whether you can use non-reweighted trajectories on MSMs, yeah, unclear. But yeah, that's a good question. And then Simon also says that the pyEMMA documentation is limited. I certainly agree with that. And he said that he found a lot of the theory on a personal blog from Frank Noe. So Frank Noe is one of the pyEMMA developers. I was not aware of his blog website, but I'm sure that that is a great resource. I think he generally describes things quite well. Thanks for pointing that out, Simon. I was not aware of that before. Here's one final thing that I think I brushed over earlier on, is that generally it's better to have more than 1 or 2 features. I know if you have some, I think the sweet spot is between maybe 5 and 20 features or so to describe some conformational transitions. When you get to have fewer features, then you're more prone to transitions that are different from what you're intending to happen, still be able to be described by the features. When you get to have too many features, then you're restricting your system far too much, and at some point, no transition is going to appropriately maximize the variance in all of those features, and it just takes way too long to even test that, because it takes so long to then load in these trajectories with an enormous number of features. They all have to get assigned to these trajectories. It takes up way too much memory as well. And so I think the sweet spot is supposed to be somewhere between 5 and 20. But again, you can definitely play around with that. So for these features, I just used 2, and I was still able to create a good Markov state model that passed all the tests and structurally showed what I was interested in. It's just supposed to be a little bit easier with more features. And I certainly did try out more features, and they all consistently failed for me, which is why I went back to a smaller number of features. But several people have mentioned before that more features is a little bit better. So I just wanted to make sure I pointed that out. Do we have any other questions, any final questions from people before we head out? Well, if we don't have any more questions, I'd say thank you all for coming, and hopefully this broad overview of Markov state modeling can be helpful. And then if any of you start to create your own models and have, more detailed questions when you're actually making them in practice, feel free to reach out to me and I can hopefully help with that.
I'll stop the recording now.
Sure, thanks.